Hello learners, in this session we are going to study Unit 12 from the second volume of NCERT textbook. The title of the unit is Organic Chemistry, Some Basic Principles and Techniques. In this session, we will talk about isomerism, fission of a covalent bond and electron displacement effects in covalent bond. The learning objectives are, after this session, you would be able to understand the concept of organic reaction mechanisms, explain the influence of electronic displacements on structure and reactivity of organic compounds. So, learners, we are starting our session with a very important and interesting concept of organic chemistry, that is isomerism. The phenomena of existence of two or more compounds possessing the same molecular formula but different structural formula is known as isomerism. Learners, do you know the term isomers come from the Greek word iso and meros means made of same parts. Thus, we can say that isomers are the compounds that are constructed from the same atoms, hence have same molecular formula but different properties. Isomerism is common among the organic compounds and it is there for the large number of organic compounds. For example, against the molecular formula of pentane, there are 3 isomers. For hexane, there are 5 isomers and for decane, there are 75 isomers. Isomerism is of 2 types, structural isomerism and stereoisomerism. Compounds having the same molecular formula but different structures, that is different arrangement of atoms within the molecule, are called structural isomers and the phenomena is called structural isomerism. Some typical examples of different types of structural isomerism are as follows. These are chain isomerism, position isomerism, functional group isomerism and metamerism. Now, we will discuss these 4 types of isomerism one by one. So, first of all, we start with chain isomerism. When 2 or more compounds have similar molecular formula but different carbon chain lengths, these are referred to as chain isomers and the phenomena is termed as chain isomerism. For example, butane and 2-methylpropane are chain isomerisms of butane. Their physical properties are also different. The boiling point of butane is 273 Kelvin, while the boiling point of 2-methylpropane is 261 Kelvin. So, chain isomers have different physical properties. Next is position isomerism. As you can see in the slide itself, when 2 or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers and this phenomena is termed as position isomerism. Their example is propane 1-ol and propane 2-ol. Learners, here in this slide, you can see a festival coat is created using bond line formula and position isomerism. Alphabet A and alphabet R are the position isomers of dimethyl cyclopropane. So, learners, be creative, make more such messages, learn academic content with such fun-filled activities. Moving on, next isomerism is functional group isomerism. 2 or more compounds having the same molecular formula but different functional groups are called functional isomers and this phenomena is termed as functional group isomerism. For example, the compound C2H6O. Against this molecular formula, we have 2 different compounds, ethanol and methoxymethane. As you can see in the slide itself, one compound is having alcoholic functional group and another is having ether functional group. Last type of structural isomerism is metamerism. It arises due to different alkyl chains on either side of the functional group in the molecule. For example, organic compound C4H10O represents methoxypropane and ethoxyethane. That's all about structural isomerism. Now let us talk about another type of isomerism, that is stereoisomerism. What this stereoisomerism is? The compounds that have same constitution and sequence of covalent bonds but differ in the arrangement of their atoms or groups in three-dimensional space are called stereoisomers. This type of isomerism is called as stereoisomerism and can be classified as geometrical isomerism and optical isomerism. Geometrical isomerism arises due to the restricted rotation of atoms of group around the carbon atom double bonds. For example, but2ene shows geometrical isomerism and exists as cis-but2ene and trans-but2ene. Like here you can see this is cis-2-butene and this one is trans-but2ene because two identical groups, they lie on the opposite side of the double bond. While here in cis-but2ene, they are lying on the same side of the double bond. Now, next topic is that we are going to discuss is fundamental concepts in organic chemistry. Here we will discuss a few basic concepts that will give us an insight of organic chemistry. In an organic reaction, the reactant molecule, also known as a substrate, it reacts with an appropriate attacking reagent and leads to the formation of one or more intermediate and then finally forms one product or more than one product. As we know, a reaction proceeds by the cleavage of bonds in reactant molecules and the formation of new bonds in product molecules. In organic molecules, the covalent bond is cleaved by heterolytic fission or by homolytic fission. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remains with one of the fragments. So, in this case, one atom has 6 electrons around it and it carries a positive charge, while the another one, a valence octet with at least one lone pair and a negative charge. For example, when methyl bromide molecule undergoes heterolytic cleavage, we get methyl carbocation with a positive charge and bromide ion having a valence octet and a negative charge. A species having a carbon atom possessing 6 electrons and a positive charge is called a carbocation. Earlier it was known as a carbonium ion, but now we are calling it carbocation. Among the carbocations, primary carbocation is least stable. Secondary carbocation is more stable than primary, and while the tertiary carbocation is most stable. Let us now know a little bit more about carbocations. Carbocations are highly unstable and reactive species having trigonal planar shape with positively charged carbon atom being sp2 hybridized. The heterolytic cleavage can also give a species in which carbon gets the shared electron pair. For example, you can see in this slide, in case of a methyl lithium molecule, methyl anion and lithium cation are formed. Such a carbon species carrying a negative charge on carbon atom is called a carbanion. Carbanions are also unstable and reactive species. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. Now learners, we will talk about homolytic cleavage. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atom. Homolytic cleavage results in the formation of neutral species called free radicals. These free radicals are also reactive species. Homolytic cleavage in chlorine molecule forms two chlorine free radicals, and homolytic cleavage in methyl halide forms methyl free radical and halogen free radical. Among the free radicals, primary free radical is least stable, secondary free radical is more stable than primary, while the tertiary free radical is most stable. Organic reactions which proceed by homolytic fission are called free radical or homopolar or non-polar reactions. Learners, after discussing two types of cleavage, now we will discuss different types of attacking reagents. These are of three types, namely free radicals, electrophiles and nucleophiles. Free radicals we have already discussed. Let us talk about electrophiles and nucleophiles. A reagent that brings an electron pair is called a nucleophile. Nucleophiles may be either negatively charged or neutral species having at least one lone pair of electrons. We can say nucleophile is a nucleus seeking species. Cl negative, OH negative, Cn negative are the nucleophiles carrying negative charge, while water, NH3 are the examples of neutral nucleophiles. Now we talk about electrophiles. A reagent that takes away an electron pair is called an electrophile. Electrophiles may be either positively charged or neutral species. For example, methyl carbocation, chloronium ion, nitronium ion, they are the electrophiles carrying positive charge, while carbonyl functional group, boron trifluoride, sulfur trifluoride are the examples of neutral electrophiles. During a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate. For example, in case of carbonyl functional group, a nucleophile attacks at carbonyl carbon, which is an electrophilic center. Learners, our next topic is electron movement in organic reactions. The movement of electrons in organic reactions are shown by curved arrow notation. It shows how the changes in bonding occur during the course of the reaction. To show the change in the position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted and it ends at a location to which the pair of electron may move. As you can see, this is quite clear in the slide mentioned there. During the course of the reaction, it may move from pi bond to adjacent single bond position, or it may move from pi bond to adjacent atom, or it can move from atom to adjacent atom. In case of homolytic fission, movement of single electron is indicated by a half-headed curved arrow. After discussing this, our next topic is electron displacement effects in covalent bonds. The bonding pairs of the covalent bond in organic compounds undergo electronic displacements, either in the ground state or under the influence of an atom or a substituent group, or in the presence of an appropriate attacking reagent. These displacements may be permanent or temporary in nature. Four types of electron displacements are generally noticed in the mechanism of organic reactions, These are as follows: inductive effect, resonance effect, electromeric effect and hyperconjugation effect. Let us start with inductive effect. Difference in electronegativity between the bonded atoms is the cause of inductive effect. For example, let us consider chloroethane. Its formula is CH3CH2Cl. As you can see in this slide, in chloroethane, the CCl bond is a polar covalent bond. It is polarized in such a way that the carbon adjacent to chlorine gains some positive charge. It is shown as delta positive charge, and the chlorine atom gains some negative charge, that is delta negative. Carbon 1, which has developed partial positive charge, draws some electron density towards it from the adjacent carbon-carbon bond. Consequently, some smaller positive charge, that is delta delta positive, develops on carbon 2 also. On carbon 2, delta delta positive is mentioned. It symbolizes relatively smaller positive charge as compared to the charge present on carbon 1. This effect decreases sharply as we move away from the atom involved in the initial polar bond and becomes negligible from the fourth atom onwards. For example, we can say that in 1-chlorobutane, inductive effect is negligible at the last carbon atom. It arises whenever an electron withdrawing group is attached to the end of the carbon chain. It is of two types: plus inductive effect known as plus I effect or electron donating effect. Alkyl groups like methyl group, ethyl group, etc., they are electron donating group. So, in a tertiary carbocation, there are 3 electron releasing groups attached with the positively charged carbon atom, dispersing its charge. Hence, tertiary carbocation is most stable, while in a secondary carbocation, there are 2 electron releasing groups attached with the positively charged carbon atom, dispersing its positive charge. Hence, secondary carbocation is less stable. In a primary carbocation, there is 1 electron releasing group attached with the positively charged carbon atom, dispersing its charge. Hence, primary carbocation is least stable. So, this is what we explained, the stability of carbocations in terms of inductive effect. Now, we are talking about minus I effect, that is electron withdrawing effect. Nitro group, halo group, cyano group, carboxyl group, ester group are electron withdrawing groups. In a nutshell, we can say inductive effect is a permanent polarization of sigma bond caused by the polarization of adjacent sigma bond. Now, we are running a video for you. So, with this video, the concept inductive effect would be more clear to you.
Inductive effect, a type of electron displacement effect. It arises because of polarization in sigma bond caused by the polarization of adjacent sigma bond. It is a permanent effect and it operates only through sigma bonds. It is of two types. First, plus I effect, shown by plus I groups such as alkyl groups. Primary alkyl groups show least plus I effect, while tertiary alkyl groups show most plus I effect. Minus I effect, which is shown by minus I groups. More electronegative atoms than hydrogen show more minus I effect. Atoms like fluorine, chlorine, bromine and iodine are more electronegative than hydrogen. For example, if there is only one electron withdrawing group, there will be less minus I effect, while if there are more number of electron withdrawing groups, there will be a greater minus I effect as shown in the figure.
So, next is resonance effect. However, before we talk about resonance effect, let us recall the concept resonance. This concept has already been discussed in chapter 4, that is chemical bonding and molecular structure. So, here we are discussing the topic in brief. There are many organic molecules whose behavior cannot be explained by a single Lewis structure. For example, the actual structure of benzene cannot be adequately represented by any one structure. Rather, it is a hybrid of the two structures where position of single and double bond alternates. These two structures of benzene are shown in the slide and they are called resonance structures or canonical forms. The actual structure of benzene is a resonance hybrid of these two structures. Now we are talking about resonance effect. Resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds or between a pi bond and a lone pair of electrons present on an adjacent atom. This effect is transmitted through the chain. The flow of electrons from one part of the conjugated system to the other creates centers of low and high electron density and facilitates the propagation of a reaction. This effect also known as mesomeric effect. There are two types of resonance effect: positive resonance effect and negative resonance effect. In positive resonance effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system, like attached to benzene ring substituents having positive resonance effect are halo group, hydroxyl group, ester group, amino group, etc. This effect is observed in the case of phenol, aniline and many other organic compounds. So, here learners, we are running a small video. You can see clearly that how positive resonance effect operates in case of aniline.
Resonance or the mesomeric effect is the hypothetical phenomena involving delocalization of pi electrons by the substituent or the functional group. Many organic molecules cannot be represented by a single Lewis structure. In turn, they are assigned more than one structure called canonical forms to explain their character and properties. Consider the benzene molecule C6H6. Each carbon atom is sp2 hybridized and forms 3 sigma bonds. The 6 2pz orbitals form pi bonds. Electrons in these orbitals are free to move around the entire benzene ring. Thus shown is the resonance structure of benzene. Now let us move on to the types of resonance effects. There are mainly two types of resonance effects, positive and negative. The positive resonance effect occurs when a group donates electrons to the conjugated system by the process of delocalization. The groups are usually denoted by +R or +M. In this process, the molecular density increases.
Now, next is negative resonance effect. This effect is observed when the transfer of electrons is towards the atom or substituent group attached to the conjugated system, that is away from the benzene ring. Substituents having negative resonance effect are nitro group, cyano group, carboxyl functional group and carbonyl group. This effect is observed in compounds like nitrobenzene, benzaldehyde, benzoic acid, etc. So, learners, here once again we are running another video showing the negative resonance effect in case of nitrobenzene.
Negative resonance effect. This effect occurs when a group withdraws electrons from the conjugated system by the process of delocalization. The groups are usually denoted by -R or -M. In this process, the molecular density decreases. Well, this was the gist of resonance effect.
Now, next electron displacement effect is electromeric effect. It is a temporary effect. The organic compounds having a double bond or a triple bond show this effect in the presence of an attacking reagent only. It is defined as the complete transfer of a shared pair of pi electrons of a multiple bond to one of the atoms on the demand of an attacking reagent. This effect is nullified as soon as the attacking reagent is removed from the domain of the reaction. There are two types of electromeric effects. These are positive electromeric effect and negative electromeric effect. In positive electromeric effect, the pi electrons of the multiple bond are transferred to that atom to which the reagent gets attached. As you can see in the slide, for example, the pi electrons of the multiple bond are transferred to that carbon atom to which the reagent H positive ion is going to attach. That is propene molecule plus H positive, giving the product species. In negative electromeric effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, as you can see in the slide, in case of propene, the pi electrons of the multiple bond are transferred to that carbon to which the attacking reagent, that is here the attacking reagent is cyanide ion, it is not going to attach. Like in case of propene and cyanide ion, you can see the effect. The last electron displacement effect is hyperconjugation effect. It is a general stabilizing interaction. It involves delocalization of sigma electrons of CH bond of an alkyl group directly attached to an atom of unsaturated system or to an atom with an unshared p orbital. Hyperconjugation is a permanent effect. It is called no bond resonance effect also. To understand hyperconjugation effect, let us take the example of ethyl carbocation, as you can see in the slide also, in which the positively charged carbon atom has an empty p orbital. One of the carbon hydrogen bond of the adjacent methyl group can align itself in the plane of the empty p orbital, and the electrons constituting the carbon hydrogen bond in plane with this orbital can then be delocalized into the empty p orbital of the positively charged carbon atom. This type of overlap stabilizes the carbocation because electron density from the adjacent sigma bond helps in dispersing the positive charge. Now here, using hyperconjugation effect, let us understand the relative stability of carbocations. In general, greater the number of alkyl groups attached to a positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of the carbocation. That is why among the carbocations, primary carbocation is least stable. Secondary carbocation is more stable than primary carbocation, while tertiary carbocation is most stable. Hyperconjugation effect is possible in alkenes and in alkyl arene also. So, here we are taking example of an alkene, that is propene. In propene, the carbon-carbon bond adjacent to the double bond acquires somewhat double bond character and hence is little shorter. Due to hyperconjugation in propene, the bond length of the carbon-carbon bond between carbon 2 and carbon 3, as you can see in the slide also, its bond length is 149 picometer, which is less than the normal single carbon-carbon bond, that is 154 picometer. Now, with this, session is over. So, quickly let us summarize what we have learnt in this session. So, the points are: compounds possessing the same molecular formula but different physical and chemical properties are called isomers, and the phenomena is called isomerism. A covalent bond can be cleaved either by heterolytic cleavage or by homolytic cleavage. Electrophiles are electron liking species, while nucleophiles are nucleus liking species. Electron displacement effects in covalent bonds are inductive effect, resonance effect, electromeric effect and hyperconjugation effect. After completing this session, let us try a few questions. So, question number 1 is, which of the two ions expected to be more stable and why? Question number 2 is, draw the resonance structures for the following compounds, that is phenol and benzaldehyde. Third question is, categorize the following molecules or ions as nucleophile or electrophile. So, learners, I am sure you must have found this session quite interesting and you must have enjoyed watching the slides and videos and studying the concepts. Thank you very much.